After completing this lecture, you can describe what is learning technique and list the most common learning algorithms. Moreover, you can explain the difference between supervised and unsupervised learning algorithms. Let's recap our framework. Given that we define machine learning algorithms as a technique to achieve the goal of learning, where learning is considered a fundamental aspect of intelligence and the overarching methodology in modern AI, then there are established techniques that have been developed in decades that brought us to this point. Later, we will show you examples of how Python programming is used as a tool to implement these techniques. We often categorize the three primary types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. This slide presents an overview of supervised learning methods, which involve learning from labeled data to make predictions or decisions. It includes, but is not limited to, classification, that is, categorizing data into predefined classes. Regression refers to predicting continuous outcomes based on input data. Semantic segmentation is about assigning a label to every pixel in an image, identifying different objects or regions. Object recognition is identifying and locating objects within an image. Another type of learning is unsupervised learning, where no label is available to learn from, and the algorithm relies on the inherent pattern in data. Famous unsupervised algorithms are clustering, that groups similar data points together. Dimensionality reduction is a powerful algorithm for the visualization of datasets. Anomaly detection is commonly used to find outlier samples in data. Density estimation is the base for generative models, where the model tries to learn the underlying distribution that governs data to generate a novel sample. In a supervised task, human workers assign the labels to each data point. Therefore, the ground truth is human intelligence. When data has label, it makes it easier for the model to learn from the labels. Or in other words, the supervision signal helps the learning process. However, the model cannot outperform the human and therefore is bound to the quality of data labels. One can see an example of data on the right side when, for the task of circle classification, the circles are labeled here using white border lines. The model learns the classification task, that is, assigning the label circle or not to the shapes. Here you can see two samples of unseen data that are not part of the training data on the right. Here the model correctly assigns the labels to these unseen samples. In contrast, unsupervised learning does not require data annotation, and therefore it's cheaper since human work is expensive. However, it is difficult if we do not even have the labels for the evaluation of the model performance, since there is no ground truth. Here for unsupervised learning, the circles are not labeled in the training data set. The algorithm takes raw data and labels the unseen data after learning the inherent pattern within the data by, for example, clustering similar-looking ellipsoids and assigning the unseen data to the relevant group. Human supervision is crucial in tasks like semantic segmentation, and object labeling, because these tasks require a deep understanding of the content within an image. Semantic segmentation involves categorizing each pixel in an image into different classes, such as cat, book, or table, which demands a precise interpretation of the visual data. Similarly, object labeling involves identifying and classifying object in an image, which requires understanding contexts, shapes, sizes, and relations between objects. Machines often struggle with these tasks because they cannot comprehend complex semantics and context the way humans do. Moreover, real-world visual data is filled with ambiguous variations and context-specific details that can be challenging for machines to handle without human input. For example, distinguishing between overlapping objects, understanding the difference between similar-looking items in different contexts, or dealing with varying lighting conditions and occlusions are tasks where human expertise is necessary. Human supervisors provide the necessary guidance, corrections, and validations that help train models to better understand and perform these tasks with higher accuracy and reliability.